Back again we are for the CR30 Programmable Safety Relay. And in this session we're going to start out talking about input filtering. Some folks call it debounce. To put in a filter that ignores any state changes that fall under a certain interval. That won't take up most of the video, and then we're going to start talking about circuits, electrical design. So let's jump right in, do some input filtering, and then start getting into the more interesting stuff, the actual electrical circuits. Let's do it. What we're looking at, we have, if you like, 3 pulse trains here. SMF input 1 and 2, and then we have the SMF output. And what we're doing is we're monitoring we're comparing input 1 with input 2. If they are both on or off for a certain length of time, then a certain thing happens. And with the input filter, we are setting a non-zero value, and during that interval we want to ignore any changes in state that are less than that interval. If we look at the first one, and that starts at 0.1, SMF input 1 is on, but 2 went off. Now, why it went off, let's say that you hit an E-stop, and 2 went off, but 1 didn't yet. Now, we're talking thousandths of a second, so don't get too caught up in the width of the graph. And then input 2 went right back on, and because this happened within time t, that's the input filter time, there's no change. And then after a little period of time, input 2 goes off again, and in this case, input 2 stayed off. So what you're basically saying is that the state of 2 was different than the state of 1 for a length of time equal to or exceeding the input filter time. And then, of course, at that point, we entered into a new circumstance where we've turned off the SMF output because 1 and 2 did not match for the length of time that was less than t. Then that meant it was a legitimate difference in state. So at 0.3, input 2 being low and input 1 being high is not a safe state. So we turn off the SMF output. And then at 4, you could say the input 1 catches up to input 2. So now they are both the same. Too late. You already turned the output off, and so now we need to reverse that, if you want to call it reset. So at 5, they both go back on. Okay, if you look at 5, 1 and 2 both go back on. However, it doesn't stay on. Input 1 doesn't stay on for a time greater than t. So it ignores it. So even though 1 and 2 were both on at the instant of 5, because they didn't stay in that state for a time greater than, equal to or greater than t, it's ignored. And then you'll see there's another pulse. So you could say that input 2 is steady and input 1 is bouncing. In other words, the switch, you turn it on, but it bounced. It made contact, broke contact, made contact, broke contact, made contact. And they both have to be in the same state for input filter time t in order for it to count. So when you get to 6, you can see at that point they are both on. Input 1 and input 2 are both on for a time equal to or greater than t. And then we enter into, we're back into a safe state, and we have one more situation there where, let's say both of them are bouncing equally, because neither one of them has changed state, or I guess you could more accurately say because between the two of them, a comparison between input 1 and 2, they were not in opposite states for a time greater than t. So it stays in a safe state. Now, that could be noise that caused that situation as opposed to switch bounce. One thing I want to say about these examples, I'm using the ones that appear in the user's manual for this product. And the reason that I'm doing that instead of creating completely different ones is that when you're in the field and you're trying to figure out what's going on with this product, you're going to go to that user manual, and this is what you're going to see by way of their explanation. So I'm going to do my best to try to clear up what you see in this timing diagram. And notice that they do have 1 through 10, that they have some text, and then up on the graph they have 1 through 10. On the graph you see pulse trains, if you want to call them that. Actually, they're just logical states or voltage states. For instance, and by the way, self-monitoring function. So SMF, input 1, 2, output, etc. Safety monitoring function is what that means. And it is a function of your programming that you do in Connected Components Workbench in the CR30. We're going to use their scenario here, and number 1, up to number 1, everything was normal. In other words, both safety inputs were on, and the safety monitoring function output was on. There was no channel fault, there was no discrepancy fault. So at point 2, after the input filter time expires, so we're still normal up until number 2. There's nothing wrong. Now you're saying, well, the input 1 is on and input 2 is off. It goes off at the point in time of number 1, but because you have a input filter time, TI, that's still considered everything's okay. So what you're doing when you configure your input filter time, you're saying, I want you to ignore any changes in state during that interval, whatever the input filter time is. Now, I'll just tell you right up front, you always want to set all of these as close to 0 as possible, and then if you start getting nuisance trips, nuisance faults, then go and make them a little bit longer to accommodate any inefficiencies or inadequacies of the contacts on your safety devices. Now, if they're electronic, they're probably not going to have any real lapse in synchronization. In other words, both inputs are going to go on and off probably at roughly the same time. But when you're dealing with mechanical stuff, or 2 contact blocks on your e-stop, and when you push it in, it changes their states mechanically. But that doesn't mean that all the contacts make and break at the same instant. And to us, it's instantaneous. But in the electronic world, a 100th of a second is a long time. So keep that in mind, that you want to keep your input filter time and discrepancy time as low as possible, as close to 0 as the system will tolerate. And if later on you get more nuisances because the hardware kind of deteriorates over time being used, you may have to make some adjustments, but start out low. So at this point, at point 2, notice that our input filter time has now expired and input 2 still does not match input 1. Do you see that? So that's the whole thing. Input 1, input 2, they don't match. But we were ignoring it for the interval of TI, input filter time. However, at that point, we now have it at 2, and that causes the safety monitoring function output. Notice that's the 3rd line down. That goes from 1 to 0. So it goes off because in between 1 and 2, it was ignoring it. The 2 was different than 1. But at the end of that input filter time, 2 is not the same state as 1, so it declares there's a problem. So it immediately shuts off the SMF output. Okay? Nothing else happens at that point. Now, I will point out right away here that the discrepancy time that you see right below the input filter time, around between 1 and 3, so forth, it doesn't come into play yet. And that's because things get changed around before it can time out. But we're showing you here that the TI and TD, they start at the same time. So if you set your input filter time longer, that doesn't make the discrepancy time longer. that means that there's going to be less time between when it makes up its mind and when you have a discrepancy fault. At 2, the system, the CR30, the logic, says there's a problem and it turns off the output. Then the input 2 catches up with input 1. They're both now the same. So the only thing you see transpiring at instant 3 is that the input 2 goes back high. So at this point, if you were just looking at input 1 and input 2, you'd say, well, what's the problem? They're both high. The problem was that when the input filter time timed out and they weren't in the same state, it turned off the output. So now you're going to have to reset the thing to get the outputs to come back on. At this point, you see that, in other words, you had input 1 was on, input 2 was off, it went back on, but it's too late, it's faulted, it turned off the output. So now both of them have to go back to off. So at time 4, notice the input 1 goes to off and input 2 both goes to off under your control. That might be that you're operating the safety switch yourself. So they have to go off in order to reset. So now we're in it, but notice that the output does not come back on just because you got the thing back under control. And I show the line green because this is a normal safe condition. We're still in a normal safe condition at input 5 when it's been reset and the output goes back on. So input 1 and input 2, they both match, they're both on, and we turn on the output. And we also turn off the channel fault that we got back between 2 and 3. Well, actually at point 3 when we got the channel fault. So that goes back off. So we're back to a normal state now, or a safe state, and things are running. The machine's running, at least for this little period right here. Input 1 now goes off, but we're still good, okay? Because we have to time out TI, the input filter time, and when we do, we created the exact same situation we had before. We turn off output, the SMF output. The difference between 1, 2, and 3, and 6, 7, and 8 here, so to speak, is in the first time, 1 was on and 2 was off and didn't match. Now, 1 is off and 2 is on. But either way, it's the exact same scenario. They don't match. This is a 2-channel safety system. So we're comparing, or I should say, the CR30 logically is comparing input 1 and input 2 to see if they are synchronized, to see if they are both the same. In other words, redundancy, self-checking. And the input filter time ignores any differences for that interval. But if the differences remain through that interval, and by the way, if the differences go away during that interval, it resets the filter time. So, and then if they unmatch again, now you're starting to time out TI again. Okay, notice that in this case, we turn off the output. So look at that red line. We turned off the output, but nothing else has happened. And then during this next interval, when we've gone past the discrepancy time, but we don't get the discrepancy fault and we don't get the channel fault. Remember, we've already turned off the output. We turned that off back there at 7. Okay, so the machine's not running anymore. The output is off. Now what we're looking at is, did the 2 inputs ever catch up with each other? And if you look, you can see at between 7 and 8, those points in time, input 1 and input 2 do not match at all. Now, at point 8, they do match. So in other words, they caught up with what you wanted, but it's too late because they exceeded first the TI, the input filter time, and now they've also exceeded the discrepancy time. So now we have a discrepancy fault, whereas before all that we had was a channel fault. And notice they both occur at the same time. And then at 9, Both inputs go low in preparation to clear the fault. Now, what made the inputs both go low? You did, or the operator did. In other words, they moved the system operator, the safety operator, either push it in, pull it out, or whatever they needed to do to reset the system. In this case, they pushed it in. So if it was an e-stop switch and the contacts weren't cooperating, in the same exact interval of the input filter time and then the discrepancy time. Remember, I told you before, I've got e-stop buttons with two normally closed contacts, and I can operate that in such a way that one of the contacts doesn't quite reset as fast as the other, and I get a discrepancy fault. They're caught up with each other. They're both off, but notice that the output is not back on. So the middle line in there, SMF output, is still off because we haven't reset. At this point, 10, after both inputs remain low for the duration that exceeds the filter time, both inputs go high, the SMF output goes high, and both the channel and the frequency faults are cleared. So you may want to use through Ethernet, you may want to capture, a timestamp on the channel faults and discrepancy faults, or even in the case where you just turn off the outputs and you quick reset it and get it back to normal. So this is the discrepancy test. And now we're back running normal. Okay, what is a safety input? A safety input, the ones that we're talking about, and I show 0 through 11. I show 12 of them. But remember that 12 through 17 can also be configured as safety inputs normally closed. They are devices with mechanical contacts such as e-stop buttons, safety limit switches, and any number of other devices. Now, this setup enables a circuit to achieve a Category 4 rating. And here is an example, a little wiring example. We have output 17. Remember, 12 through 17 are unique because you can configure 12 through 17 for 5 different functions. But we've configured 17 configured for a pulse test output. Our e-stop button is not going to 24 volts DC. In other words, when the e-stop is pulled out and the normally close is closed, we are not feeding 24 volts DC to terminal 0, input 0. We are feeding a pulse train from 17 through the e-stop button to 0. So in order to get a Category 4 rating, you have to use a pulse test output instead of a 24 volt high side to the monitored contact, which that's mostly what they do in the older, we'll call it master control relay days. We would have used a line voltage of some sort through the contacts of the e-stop to power the coil on the MCR. And then along came palm buttons and anti-tie down, and then the rudimentary safety relays that originally, or before the safety relays, you used a number of relays to create a safety relay circuit, but there was no safety relay. It was just a very convoluted circuit. So instead of a 24 volt DC high side to the monitored contact, the CR30 output applies an encoded high side. If the input terminal 0 does not see, in other words, decode what was encoded on 17, the controller declares an invalid state for input 0. That is a safety input. And you could say this is almost analogous to the modulated light source that optical sensors like photo eyes use to ignore extraneous light sources. If you know anything about photo eyes, the good ones, it's not just a light source like a light bulb. It is a modulated. In other words, the light is going on and off at a specific frequency. And if the receptor, the receiver, doesn't see light at that exact frequency, it's as like it doesn't see any light at all. So most photo eyes now, the light source is encoded and the receiver, or you could say the transmitter, is encoded and the receiver decodes it. Devices such as light curtains, laser scanners, solid state interlocks like I'm using on the project that I just went over here in the last month or so, they have OSSD inputs. And these have built-in test pulses or other methods of fault detection. These devices are connected directly to the inputs of the CR30 and do not use a test output because they generate their own test output. Make a note, these devices must have a common reference with the CR30 safety relay. So notice that, it says must have common reference. So you see that both negative sides of the receiver and the transmitter of the light curtain, they go to the same common that's used for the CR30. So these safeguarding devices with OSSD outputs generate their own test pulses to detect for short circuit conditions or have other methods. When you configure your CR30 for dual channel OSSD, the CR30 safety relay ignores the test pulses. So it's all taken care of for you. You're going to notice when you start programming this device that when it comes time for you to select something, it's not going to let you open up the whole drawer and pick anything you want. It's only going to make available to you what you can pick that's legitimate. When we continue in the next video, we will actually get to the circuit designs, the actual electrical design, and we're going to go through as many as we can and discuss them. Thank you for watching.